So today we'll begin learning about even more kinds of regions over which we can do double integrals with the aid of polar coordinates. And so we take a look at a region like this here, denoted A, this region of area A, and it's part of a washer. We have an inner circle that's missing, we have an outer circle boundary, and then we have straight lines of constant theta forming the boundaries of our region here. And so the big question that we want to investigate today is if there's a straightforward way to do integrals over regions like this that look like they would be very easily expressed in polar coordinates. So based on the ways we've seen so far in Cartesian coordinates, slicing either in X for a type 1 region or Y for a so-called type 2 region, each approach would be awkward for this case. So if we had to slice in X, create regions where we had vertical slices, that would be awkward because we'd have to divide the domain into 3 pieces. We have this piece here where the domain consists of these top function and this bottom function here. But then in this middle region, the bottom function changes while the top stays the same. And in this third region, the top function changes and the bottom function stays the same. And the story is the same if we slice in Y. We'd have to change into 3 different regions, each of which would be sort of complicated to express in terms of X and Y. But suppose we were able to slice in theta. This line here is a line of constant theta, part of a washer. Here's a line of constant theta, and we could imagine drawing other lines of constant theta that rotate through the washer here. And that looks pretty simple. So we'd like to be able to do that in this kind of situation. So the question is then, how does this work if we do this in polar coordinates? Okay, so it looks very much like polar coordinates, but how do we use polar coordinates and do integrals in polar coordinates? And as is often the case, it's most straightforward simply to go back to basics, to a formula that we may not quite like, but that nevertheless makes it pretty clear how to do this. And that's to recall that the integral itself is nothing more than a shorthand notation for a Riemann sum. So what happens if we take a region like this and we slice it in theta, and then we slice it in R like this, so lines of constant R, lines of constant theta. We have these small areas inside delta A associated with a small change in R, delta R, and a small change in theta, delta theta. And we break the domain into these regions. We multiply the value of the domain in each region times the area of each of those little domains, and that gives us a volume. And then we add them all up, and then we take that sum and we take the limit as delta R and delta theta go to 0. So the only real question it looks like we need to answer, all of this bit here looks exactly like we would expect, sum over small intervals in R and theta. The only thing it looks like we need to answer is this part here. What is delta A ij in terms of R, theta, delta R, and delta theta? And of course, once we figure that out, then in the limit, this delta A notation will turn into a dA notation. So these are really equivalent questions. What is delta Aij? Or in the limit as delta R and delta theta go to 0, what is dA? So let's think about this in more detail. So here we have a region of just this type, a small change delta theta in theta and a small change delta R in R. And we have actually formulas that we can apply for this kind of area. So the area of a circular wedge, that would be the whole region here, the area of a circular wedge is given by the formula 1/2 delta theta R squared, where R is the outer radius and delta theta is this, this interval here in theta. And you can see right away that if delta theta is 2 pi, that is if we include the whole circle, then this area becomes pi r squared, the area of the whole circle. But the area of just a wedge or sector of a circle is given by 1/2 delta theta R squared. And the way to find the area of our particular delta A right here is to simply subtract the area of a wedge with radius R plus delta R minus a wedge with radius just Ri. Okay, and so we write that down. So the area of our little square, delta Aij, for the ith slice in R and the jth, the ith slice in r and the jth slice in theta, I've got that mislabeled here, is 1/2 delta theta larger radius squared minus 1/2 delta theta smaller radius squared. This has the form a squared minus b squared, which can be written a plus b times a minus b. A plus b in this case would be ri plus ri minus delta r, so that's 2ri plus delta r. And a minus b would be ri plus delta r minus ri, or just delta r. So we can write that in the form 1/2 delta theta, 2r, the 1/2 here cancels the 2, and we get an ri delta r delta theta. And for this term here, we get a 1/2 delta r squared delta theta. And the fact that this one is delta r squared, while this one is delta r, is very important because we are taking the limit as delta r and delta theta go to 0. So when we take that limit, if delta r is very small, then delta r squared is even smaller. And in the limit as delta r goes to 0, this second term can be neglected in comparison to the first. And so the delta A, the area of this slice, this square, approximate square, as delta r goes to 0 becomes just the first term, ri delta r delta theta. And so in that limit, we can replace the notation delta A with dA, and we find that dA is r dr d theta, which is something that you may have heard of before. But this is where this formula comes from. It comes from having to calculate inside the Riemann sum the quantity delta A. What is the area of a little square when I slice my domain up into pieces? And the area of such a little square, if it is sufficiently small, approaches r delta theta, or r dr d theta when we switch to integral notation. So here is our main result. This area element, as it's called, dA, is written in polar coordinates, not as dx dy, not as dr d theta, which you might have guessed by analogy, but rather r dr d theta is how we write dA in polar coordinates. That's what we just derived. And with this result, we are now ready to do integrals in polar coordinates of functions of r and theta. Okay? So for instance, suppose I have this integral right here, the integral of r dA, where d is the unit circle. This is going to be the area underneath a cone sitting on its nose. So this is like z equals r, and that's, if you think about it for a minute, it doesn't depend on theta, so it's like a cone, the line z equals r wrapped around the z-axis. So it's like a cone sitting on its nose, and it's the area underneath that cone, not the area of the cone itself, but the area under the cone. So as in the previous problems, even in polar coordinates or any coordinate system, the next step is to figure out what the bounds of the domain should be. And so what is the unit circle? The unit circle is all values of r less than 1, so r lies between 0 and 1. And theta goes all the way around the circle, so it's 0 to 2 pi. So this pair of limits defines the unit circle, which we could understand from looking at a drawing of the unit circle. And so this integral of the double integral of r dA on the unit circle becomes the integral r goes from 0 to 1, theta goes from 0 to 2 pi of r times dA, and dA becomes r dr d theta. And we've been very careful that our r bound here is done first, and our theta bound is on the outside done second. So again, inside out. And now it's just a series of plain old iterated integrals like we did in x or y. These just become symbols, and it doesn't matter whether they're x or y or r or theta or any other symbols. It's a plain old integral. I've cast dA into the appropriate set of variables, and so now I just proceed. So I have on the inside the integral from 0 to 1 of r squared dr, and then I have on the outside the integral from 0 to 2 pi of the result d theta. Well, the integral of r squared is 1/3 r cubed. From 0 to 1, that's going to give me just 1/3. And now when I integrate the constant 1/3 from 0 to 2 pi in theta, that's just going to give me 2 pi times 1/3, so 2 pi over 3. Again, that's not the area of a cone, which you might have expected 1/3 in there somewhere, but the area under that conical surface. So it's 2/3 pi. So that's great. We can now do integrals of polar functions in polar domains. But suppose you're given a function that's in terms of x and y in Cartesian coordinates, and yet the domain is, say, a circle or some domain that's best expressed in polar coordinates. What we can do is simply change the integrand from being a function of x and y to being a function of r and theta. And we have the relationships between the Cartesian coordinates and the polar coordinates. X equals r cosine theta and y equals r sine theta. Those are always true in any context. And so we can use them to turn this integrand here into an integrand involving r and theta. So we already saw that the domain is r going from 0 to 1 and theta going from 0 to 2 pi. We're again here on the unit circle. But now we take this the polar coordinate relations and turn this x into r cosine theta. And so the double integral of x dA on the domain D becomes r goes from 0 to 1, theta goes from 0 to 2 pi of r cosine theta, r dr d theta, where again I've got my r bounds on the inside to go along with dr and my theta bounds on the outside to go with d theta. We can mix this up. We can do this a little bit differently. We've seen already that if you have a separable integrand that is a function of r times a function of theta, that you can pull the function of theta outside the r integral and the d theta as well, and we have just the product of two integrals. So this is indeed separable. We can break this into the product 0 to 2 pi integral of cosine theta d theta and integral from 0 to 1 of r squared dr. And so the former is negative sine theta from 0 to 2 pi, and the latter is 1/3 r cubed from 0 to 1. This would contribute an amount 1/3, but sine of theta is 0 at both 0 and 2 pi, so this term is 0, and so the whole integral is 0. Where does that come from? Well, x, just to sort of a partial check on our answer, x is an odd function of x. And so the unit circle is symmetric with respect to x. You have 1/2 of the unit circle over here in positive x and 1/2 in negative x. And the contribution of positive integrand over here is exactly canceled by the negative integrand over here. And so the two sides cancel each other out to give us 0. So there's an example of changing variables in an integral, which is an important concept. We had an integrand in one kind of coordinate system, and we converted it to another coordinate system because the boundaries were more easy to do in the other coordinate system. And that's a theme that we'll see many times in this class. So a couple more things. So we saw in Cartesian coordinates that our domain didn't need to be a rectangle. So in polar coordinates, our domain does not need to be a slice of washer. So analogous to the so-called type 1 and type 2 in Cartesian coordinates, there are two common ways of having non-straight or non-simple domains in polar coordinates. The one is where we slice in theta. So theta is sliced and we have boundaries of constant theta, theta 1 and theta 2. But the boundaries in the r direction, we have a lower function g of theta, an inner function g of theta if you like, and an outer function h of theta. And so this can be expressed simply in terms of bounds. Theta goes from theta 1 to theta 2, and r goes from g of theta to h of theta. And we can write that down on our integral bounds. R goes from g of theta to h of theta, theta goes from theta 1 to theta 2, r dr d theta, and we're careful that our r bounds correspond to r being on the inside. Similarly, to a type 2, we could, instead of slicing in theta, we could slice in r. So we could draw curves of constant r, slicing r into pieces, an inner boundary r equals r1, an outer boundary r equals r2, and then we could have theta equal some function of r, h of r, and on the other side, theta equals some other function, g of r. So again, theta could go from, g of r and h of r, and these are backwards too, or rather, they're not consistent with here. So the way I've drawn it should be h of r to g of r d theta, and r goes from r1 to r2. And in this situation, we must do the theta integral first because the bounds on theta depend on r. And so instead of r dr d theta, in this situation, we have to write r d theta dr. So let's do an example of that where the bounds are not constant in both r and theta. Let's just integrate a constant function. So let's focus on the boundaries and make the function simple. So we'll do an integral of the function c, just a constant, dA, where the domain over which we're integrating is a unit circle centered at the point x equals a with radius a. So that's this unit circle right here. And we're integrating the constant c. So what this really is we should be finding the volume of a cylinder. Here's the domain, now projected in 3 dimensions. Here is our constant height c, and so this should be some cylindrical object. And if we redraw the domain in the xy plane, we see that this circle ought to be r as some function of theta. That all these lines where we're slicing in theta start at 0, and then they go out to some value r as a function of theta. And so our bounds on r should be 0 to some function of theta. So our first job is to figure out what function that is. How can we express this circle in polar coordinates, right? Here the domain is expressed in Cartesian coordinates. How can we express this circle centered at x equals a in terms of polar coordinates? So take this equation here and change all the x's and y's to r cosine theta and r sine theta. And what do we get? We get r cosine theta minus a, quantity squared, plus r sine theta squared equals a squared. We'll write all that out. We get 3 terms from the first. The second squared equals a squared. We'll get a cancellation of an a squared. We will also get an r cosine squared plus r sine squared, which will just make us an r squared. So we get an r squared minus 2r cosine theta a equals 0. And that has 2 solutions for r. We could either have r equals 0 or r equals 2a cosine theta. So these are the 2 values of r that satisfy the equation for the circle. And we recognize these first one as the boundary. We said all these lines start at r equals 0. So this second one must be the polar equation for this shifted circle in polar coordinates. So there's r. The bounds on r depend on theta. But what are the bounds on theta? So if we redraw this sketch, it looks like this only occupies the 4th and 1st quadrants. And so this is the region where theta goes from 0 to pi over 2, and here it goes from negative pi over 2 to 0. So it looks like we only need minus pi over 2 to pi over 2 to complete this circle. Okay, it's not always the case that we need all the way from 0 to 2 pi. So let's write this integral out. The integral is now the integral of c r dr d theta, and I write dr d theta because I first do r goes from 0 to 2a cosine theta, and then at the end, theta goes from minus pi over 2 to pi over 2. So there's a little bit of manipulation that we have to do here. We first integrate r dr, and we get 1/2 r squared, which is evaluated from 0 to 2a cosine theta. So that's going to be 1/2 2a cosine theta quantity squared. That's what I've written here. Now I have to convert this to something that I can integrate in theta. I'll first pull out all my constants. My 2a quantity squared will give me 4a squared, but when I multiply by 1/2, I'll get 2a squared times c. So all my constants are right here, and all I'm left with inside this parenthesis is a cosine squared. Now you can't integrate cosine squared straight away. You have to use a half angle identities to set it equal to 1/2 1 plus cosine of 2 theta. This we can now integrate. Again, I'll combine this 1/2 with a 2. I'll get a squared c. And when I integrate 1 plus cosine theta, I get cosine 2 theta, I get theta plus 1/2 sine 2 theta, which is evaluated from minus pi over 2 to pi over 2. The theta is pi over 2 minus pi over 2 minus negative pi over 2. That gives me pi. Sine of 2 pi over 2, that's sine of pi, which is 0. Sine of 2 negative pi over 2, that's sine of negative pi, which is also 0. So this term gives us nothing, and all I'm left with is pi a squared c, which as we should expect, pi times the radius squared times the height gives us the volume of that cylinder. I'll do one more example. That may make the video a little bit long, but it's a great example of this kind of stuff, and it's an important example that you should learn at some point so that you know how to do this very important integral. We won't focus on this particularly much in class, but it's worth your time for the next couple minutes. So this function, e to the minus x squared, is one of those functions that has no simple antiderivative. There's just no way you can integrate that using integration by parts or substitution. Either of these two techniques doesn't really get you anywhere. But it is so common, it's such a common function, it comes up all the time in probability theory, in the normal distribution, and many other places, that we often need to be able to deal with integrals of this function. And for this purpose, we have in fact invented a new function called the error function, which is defined to be the integral of e to the minus x squared dx. And this function can be calculated using Taylor series. We can break this down into Taylor series and integrate it term by term, and we can call the result the error function. So that's fine, but there are certain cases, even within needing to do this, where we need to do a very particular integral of this, and that's the improper integral of e to the minus x squared from minus infinity to infinity. So that would be this. Here is this thing. It's called a Gaussian function, and here it is. It has a bump in the middle. It decays to 0 on both ends, and we want to find the area underneath this all the way out to infinity, which is an improper integral that we learned how to do in Calculus 2. So here's the trick. First, there's a trick. You don't need to learn this trick. I'll just show it to you. It's not something that you need to worry about, but it's something that works particularly well in this problem. And the trick is to say, okay, I've already decided that I cannot do this integral I. I'll call it I. So what I'm going to do is square it. I squared is this integral times itself. So I've just rewritten integral times the integral. And then, here's the really tricky part, is that inside this integral, x is just a dummy variable. Inside this integral, x is just another dummy variable. And it doesn't matter what that variable is. It could be anything at all. So I'm going to change it to y in the second case. E to the minus y squared dy from minus infinity to infinity. And now, this is two integrals, and so I can combine them into a double integral of a separable function. And so I can combine them into the double integral minus infinity to infinity of e to the minus x squared times e to the minus y squared, which can be combined e to the minus x squared plus y squared dx dy. Now, I originally thought of this just as one integral squared, but here I have a dx dy sitting there, so let me just think of this as now a double integral over some area, which consists of the whole real number domain. I'll call that dA, e to the minus x squared plus y squared dA. So if I can calculate this area integral, then I can just take the square root of it, and I'll have my original thing I. Okay, now, here's where the magic happens. Let me call this now, let me think of it now in polar coordinates. Here I have an x squared plus y squared. That's going to become an r squared. So that's handy. And here I have a dA. We already figured out what dA is in polar coordinates. It's r d theta. So that becomes this right here. And the only thing that's necessary to do then is to change our bounds. So instead of x and y going from minus infinity to infinity, both of them, the whole domain of all the real numbers should be expressed theta going from 0 to 2 pi, so all the way around the circle, and r going from 0 all the way out to infinity. R does not go to negative infinity. It starts at 0 and goes outward to infinity, and this is the whole plane. And you've probably already seen why this helps us, because now I can use a u substitution. This becomes something where I can do a u substitution. I guess I've separated it first. I've done an r integral, e to the minus r squared r dr from 0 to infinity, times 0 to 2 pi integral of just d theta. That integral from 0 to 2 pi of d theta becomes 2 pi. And this integral here in r I can now do by substitution. I can say u equals r squared, du equals 2r dr. That means I have half of a du of e to the minus u du. I did change my upper and lower bounds. It's just that they remain the same under this function. So when r equals 0, u is 0. So the 0 remains 0. And as r goes to infinity, u also goes to infinity. So this is not a mistake. It's that the bounds remain the same when I perform this change of variables. And finally, I can do this integral simply. It's just, I can pull that 1/2 with the 2 and make a pi, and this becomes negative e to the minus u, 0 to infinity. At infinity, this becomes 0, and when I subtract a -1, I just get pi. So the area integral is pi, and that means the very thing I wanted to find at the very beginning is the square root of pi. And so we can now say that this integral, that from minus infinity to infinity of e to the minus x squared dx, you can always say it's the square root of pi. And we found it using integrals in polar coordinates.